Forest fires are a natural part of the ecosystem. However, they can have devastating effects on the local environment and economy. For example, forest fires can kill animals, plants, and trees and also release toxic gases into the air. Now, when it comes to fighting forest fires, the key is to contain them. However, this is difficult because most fires spread too quickly and are difficult for a single fire group. Therefore, to address this issue, we are developing a multi-robot system prototype that would assist in the early detection and tracking of the wildfire hotspots in the forest. This prototype comprises a combination of drones as well as a GSP that work in coordination to tackle the calamity at hand. This is the block diagram for our prototype. The central processor at the center is the brain of the system. Both the Camel as well as the surveillance drones and the ground support vehicle are in communication with it via the NRF transceiver modules. And also the video feed from the drones as well as the ground support vehicle are transmitted using the AV transmitters. So the main objective of the surveillance drone is to provide live feed of the area and also provide coordinates in event of an emergency. The Camel drone, on the other hand, will do the heavy lifting and carry necessary supplies to the site. Finally, the ground support vehicle, which is on the ground, will provide the ground level intel on rescue and make the rescuers aware of the situation before the start of the rescue operation. So, there were a couple of tests that were conducted while working on the drones. In the first video, we are running a test for all the BLDC motors, and these motors were selected based on the RPM, the thrust provided and the training ratings. Then in the second video, we have designed a CAD model of the drone using the SolidWorks software. In the third video, the MPU6050 sensor is being tested for its accuracy and precision. And finally, in the fourth video, the proportional, integral and differential PID constants are being tuned on the rig. Now, these are a couple of clips showing the tests that were conducted for calculating the PID parameters with respect to the angular variables, yaw, pitch and roll of the drone. In the first and second video, the PID parameters for the yaw and pitch motion are being calculated, and in the third video, a ground test is being conducted without setting the roll parameters.
This block of code takes the inputs from the Xbox controller and maps them into the desired set points. Here, the angles received from the IMU act as the input for the PID controllers. Then, the speed of individual motors is calculated on the basis of the output of the PID controllers. The debug function is used to display the important variables for analysis of the performance and debugging. This file contains the code for extraction of the current gyroscopic orientations of the drone. The MPU is interfaced with the Arduino via I2C protocol. The raw gyroscopic data is converted into YPR values in degrees that are used by the PID controllers.
This video demonstrates the first prototype of the ground support vehicle. The bot has a TF Luna LiDAR sensor mounted on the servo that moves to 9 fixed angles. The distance at each angle is stored in an array. The largest distance in the array suggests the path with obstacle at greater distance and can be used to direct the path of the vehicle. Arduino Uno along with L298D driver shield was used for the prototype.
This code snippet takes the video feed from the webcam of the laptop and extracts the frame from the video as an image. Then each frame is fed to the trained CNN model to predict whether the image contains fire or not. Here, an image of a forest fire is shown to the webcam from another device. It shows the output as fire whenever the image is seen in the video frame. Otherwise, the output is shown as no fire. However, the model gives a false positive output for a few red or orange colored objects as well. This will be improvised in the later stages.
An RF24L01 transceiver module were tested using the radio and radio head library of Arduino Uno. Each action of joystick is passed over a particular channel. The data sent on each channel is acknowledged with a response. Motor A changing value I repeat, motor A is changing value. Motor A value becoming 0. Motor A changing value. Motor B. Motor A. Then in the second part of the video, the value of the joystick is shown on the 128x64 pixel OLED screen. The command from the transmitter side can be used to operate the change in the path of the bot if needed.